Molweni guys. I hope niyaphila. Guys, I want to do a sincerely apology. I've been listening to your comments, especially on the Electrotechnology N3 DC machine calculations. Okay, a subscriber written there, but I should try more and communicate in English, of which is I'm learning from you guys as you comment. Yeah, but as I am still new in this platform, so it made a lot of sense because not all my viewers speak Zulu or Xhosa. Yeah, but so I decided it's a good thing and it's a good advice, yeah, because English is the learning language. It's the international learning language. So I decided as an apology to redo the session on electrotechnology, DC machine calculations. Okay, so guys, the first thing when you speak of a DC machines, we're speaking in terms of electrical terms. When you speak of machines, it's either we are speaking of a generator or we are speaking of a motor. Okay, okay, okay. We know that a generator, it's mechanically driven and it produces electricity as an output. Then we know that a motor, it is supplied with electricity, then gives us mechanical energy as output. So these two machines operate vice versa. Okay, so now that we know the two types of machines, which is the generator and the motor, so we'll be talking of DC machines, okay, meaning the generator generates direct current electricity, meaning the motor is driven by direct current electricity. Okay, so the first thing I want us to do is do the EMF equation of DC machines. Okay guys, the first equation that I want us to first talk about EMF equation now is the general EMF equation. Okay, guys, if you can see the statement that I'm making here, I am saying this is a general EMF equation. So it meaning that this equation that I'm gonna write down is practically used both for a DC generator and a DC motor. Okay, the only difference that let's say if we are talking of a generator, okay, if we are talking of a generator, E, which is basically the EMF, is the generated voltage, or the open circuit voltage is the generated EMF, guys. Okay, this is the voltage, or this is the induced EMF in the armature of the generator. Okay, which is the generated EMF, is the induced EMF in the armature of the generator. In terms of motor, okay, guys, in terms of motor, this E, which is the EMF, is the back EMF. Okay. Uh, this EMF opposes the supply voltage. Remember, in a motor we have to supply it with a potential difference, or we have to supply it with a voltage. So we have to have a voltage supply. This EMF is the back EMF and is generated because as the motor starts spinning, it is basically cutting the lines of flux and is generating electricity that is opposing the electricity that it is getting from the source. Okay, this back EMF is not basically a disadvantageous. It's basically advantageous because it allows for the regulation of the armature current. Okay, let me write down this general EMF equation that I'm talking about. That is practically used for both motor and generator. This equation is given by E is equals to 2P flux N Z over 60 C. Okay, now guys, let us look at each quantity individually. Okay, E is, we know, it is the EMF, né? Then P is the pole pair. Okay, pole pair, guys. Okay, what do we mean by a pole pair? Guys, a pole pair is made by a north pole and a south pole. So if I have a 4-pole motor, that means I have 2 poles. Sorry guys, I meant to say if I have a 4-pole motor, that means I have 2 pairs of poles, which is 2 north, 2 south. Okay, so if I have a 6-pole motor, that means I have 3 pairs. Okay, so it's basically the pole pair is basically the total number of poles of the machine divided by 2. Okay, that is pole pair. Then you get your pole pair. You take the total number of pole of the machine, then you divide it by 2. Then the next one is useful flux pair. Okay, sorry, before I continue, the pole pair does not have a unit, guys. Okay, this one will have a unit, which is the useful flux per pole. Okay, this is measured in Webers. Okay, or in most instances it's in milliwebers. Okay, the next quantity is the speed. Okay, which is measured in revs per minute. Okay, in the case of a generator, guys, this is the speed at which the generator is driven. Then in the case of a motor, this is the speed at which the motor is running. Okay, then the next quantity is Z, which is the number of armature conductors. Okay, the number of armature conductors. Okay, then the last quantity is C. C is the type of armature connection. Okay, type of armature connection. Okay, as we know, guys, there are 2 types of armature connection. that is the lamp or wave. Okay, I won't dwell much on this because in this section I wanted to cover only calculations. Um, in case of the lamp connection, C is equals to 2P. Now that is for the lamp connection. Then in case of the wave connection, C is basically just equals to 2. Okay, so guys, what does this mean? In terms of the lamp, it basically means that C is equals to the number of poles, because remember now you are saying 2 multiply by the pole pair, which is basically this is equivalent to total number of poles. Okay, so guys, that is it. That is the general EMF equation. Okay guys, before we move on, I want us to firstly observe something about the general EMF equation. Okay, okay, if you look at these quantities now that we use to determine either the EMF equation of to determine the EMF of a generator or the EMF of a motor, you'll see that most of these quantities that are put in this equation are basically non-electrical quantities. For example, what do I mean? For example, if you look at P, for example, P, that is a pole pair, that is non-electrical. Then useful flux, that is non-electrical. Then speed is non-electrical. Even number of conductors is non-electrical. So guys, this equation, the reason that is being practically used to determine the EMF equation of either the generator or the motor, it is mainly because it is derived based on the construction of the machine. It is derived based on the physical construction of the machine. It's not like the next set of equation that we'll be writing down just now, because those equations are derived from electrical principle, electrical laws. Okay, the equation that I'm talking about is the specific equation for a generator and the specific equation for the motor. Okay, and the equation that I'm gonna write down now are derived based on electrical principles. Okay, that is the first one, the EMF equation. EMF equation. Sorry, EMF equation. EMF equation for generator. Okay, and the law that I'm talking about, guys, is Kirchhoff's law. Okay, as we know, there are two Kirchhoff's law. There is the voltage law, and there is the current law. So basically, because we are talking of EMF equation, this equation is derived based on Kirchhoff's voltage law. Okay, so the equation goes as follow. If you want to calculate the EMF of the generator, we say V plus I A R is RA. Okay, if you look at this equation, there are only electrical values here, which is the voltage, the current, armature current, and the armature circuit resistance. Okay, in case of a generator, as I've said, in case of a generator, E is basically the generated, or you say the induced EMF. Okay, okay, that is the voltage that we generated in the armature. Okay, then guys, V is basically the terminal voltage. It is the voltage that you get at your output terminals. As you know, okay, guys, this terminal voltage now would be slightly lesser than the EMF, because what we generate is not what we'll get at our output due to the internal voltage drop. If you remember when we're describing the EMF of a battery and the terminal voltage, if you take a battery and measure the voltage, you see that you get a higher value when the battery is not connected into any circuit. Okay, uh, when you connect it to a circuit, you get a slightly lesser value, because a battery has what we call an internal volt drop. So this is the same case. A generator, DC generator, has an internal voltage drop due to the resistance of the armature windings. Okay, um, what voltage drop I'm talking about in this one? IA RAC. Okay, this one RA IA RAC. That is the voltage drop. Voltage drop across uh, the armature circuit. Okay, that is the voltage drop across the armature circuit. That is why you would get a lower voltage. That is why uh, V, the terminal voltage, is less than the generated EMF, is because of the internal voltage drop of this DC generator. Okay, we know IA is the armature current, then RA is the armature circuit resistance. Okay, um, that is it for the EMF equation of a DC generator. Now let us look at the EMF equation for the motor. Guys, it's basically the same equation, but the sign differs. Case E is equals to V minus IA RAC. Guys, I remember again, I've said it that E is basically the back EMF and E opposes the supply voltage. So guys, E is the back EMF when we are talking of a motor. Then this V is not, this V is the supply voltage in this case, because remember we are supplying the motor with electricity in order to get mechanical power. Okay, so V is the supply voltage in case of the motor. Then in case of the generator, we said it's the terminal voltage. Okay, then then IA RA is basically is the same, is the voltage drop across the armature. Okay, then IA is the armature current. Then RA is the armature circuit resistance. Guys, these are the specific EMF equations. Take note of that. Okay, it means, guys, I cannot use this equation in a generator. Okay, the equation for a generator, the sign is what? Positive. Then for the motor, the sign is what? Negative. Okay, then now let us look at, I want us to look at two types of DC generators. Okay, or based on these two types is because they are the ones that we do calculations on. Okay, they are the ones that we do calculations on, and these two types are the series and the shunt. Okay, these two types, they are the series and the shunt. So I want us to analyze the current flow and the voltage drop and stuff because it is critically important. Okay, let me start off with a series machine. Okay, with a series machine. Let me start off with the series machine being operated as a generator. So basically, I'm starting off with a series generator. Okay, series generator. Okay, okay, guys, why am I drawing current originating from the armature? Remember, this is a generator. There, where are we generating this electricity? We are generating, guys. This electricity at the armature. Okay, so the source current is basically the armature current. Okay, okay. Now let us continue looking at the currents. This is I series, then this is I load, the load current. Okay, the load current, you'll only get it once you connect a load. Maybe you connect a lamp or you connect a kettle, whatever, this generator will be supplying. Okay, guys, up and we can safely say that the current is the same. Okay, nothing's changed. This is a series circuit, as you can see right in front of you. So IA is equals to IL is equals to I what? Series. Okay, that is a fact based on what we know about a series circuit. Then the armature circuit, let me write it as RAC because this is R. Uh, remember, even the series field winding has resistance. So R, which is the armature circuit resistance, is basically equals to RS plus RA. Why, guys? It is because the armature and the series field winding are connected in series with each other. Basically, meaning that uh, this, sorry, basically meaning the resistance of this winding is part of the armature circuit. Hence, that is why I have to add it to the armature circuit. Okay, that is the series machine operated as a generator. Okay, let us look at the series machine now being operated as a motor. Okay, okay, guys. This is a series machine now being operated as a motor. Notice where I will draw my source current. Okay, my source current is coming from the supply. It's coming from the supply, guys. Why? Because remember now I'm supplying this machine with electricity. Okay, in order to get mechanical or to get motion out of it. So basically, I am operating it as a motor. Okay, so IL is the source current this time. Then you have I series. Then you have I armature. Okay. With the fact this is a series machine, it means it's a series circuit. So I series is still equals to IL, still equals to IA. The current is the same. And the armature circuit resistance, guys, is RS plus RA. Nothing has changed. The only thing that is changed is the direction of the current and the source current. IL is the source current. Okay, then let us look at the second type of machine, that is the shunt. Sorry, that is the shunt machine. Okay, in the shunt machine, we have the field winding in parallel with the armature. Remember, I taught you that. Okay, so let us say that this shunt machine is operated as a generator. Okay, you're sorry, I'm drawing a series generator now, guys. Ish. Okay, sorry. I was supposed to be drawing a shunt generator. Okay, there we go. Okay, okay. Now, guys, because this is a generator, where is the source current going to come from? The source current is gonna come from the armature. Okay, so here is my source current, IA. Okay, then it splits into IL, then I shunt. Okay, uh, then we have the terminal voltage. Guys, I cannot do what I did to the series here because this is a parallel connection. I cannot say IA is equals to I load is equals to I shunt. No, these currents are not the same. These currents are not the same, guys. So what do I do? I'm gonna apply Kirchhoff's current law, which is KCL, which is KCL. Kirchhoff's, Kirchhoff's current law states that the current flowing towards a junction is equals to the algebraic sum of the current flowing away from that junction, of which is there are two currents that are flowing away. There is only one current flowing towards. That is the current that is flowing towards the junction. This one is IA. IA is basically I load plus I shunt. Okay. Remember, guys, um, I shunt can also be calculated in terms of Ohm's law, which is V over R shunt. Okay, but please, guys, never use this equation. VIA is equals to V over RA. Please never use this equation. I will explain in future why you don't use that equation. Okay, because it's based on it's, it's more based on the armature when it's rotating. And okay, basically when you talk of a motor, it's more based on the effects of the back EMF. Okay, but please for now don't use that equation, please. Then uh, um because okay, let me just explain it now. The armature current is basically equals to, in case of a generator, okay, um, in case of a generator, we can say is equals to V over RA. But this is only applicable when the motor, sorry, the generator is at a standstill. But when it starts rotating, it's no longer applicable. Okay, please don't use that equation to be on the safe side. Then guys, the armature circuit resistance here, RAC, is only equals to RA. It cannot be equals to RAC is equals to RA plus R shunt. Why, guys? Because remember, the shunt winding is not part of the armature circuit. Okay, you don't include it when you are calculating the armature circuit resistance. Okay, the only thing that we have in the armature circuit is the armature only. Okay, then let us look at in terms of the motor. Okay, in terms of the motor, in terms of the motor, in terms of the motor, guys, in terms of the motor, let's draw the shunt motor. Okay, there is my shunt motor. Because it's a motor now, guys, the current, which is the source current, is coming from the supply. Remember, a motor is supplied with electricity again. And then there's I load, this is I armature, this is what? I shunt. Okay, notice, guys, the source current is the load current. Basically, guys, meaning which I load is equals to I armature plus I what? Shunt. Okay, so now let me put the armature current as subject of the formula, because the armature current is the one that I will want to calculate. Why? Because I use it to determine the EMF of uh, of a generator or a motor. So IA in terms of the motor is equals to I load minus I shunt. Let us compare that with the armature current of the generator. You see, with the armature current of the generator, you use a plus sign, but with the armature current of the motor, you use a minus. Okay, and RAC is still equals to RA only, because this winding is not part of the armature circuit. And um, um, what else am I forgetting? And the shunt current can be calculated by what? Sorry, by V over R shunt. Okay, and then in terms of armature current, I said don't use this Ohm's law equation, V over RA, because in a motor there is a back EMF. Okay, the true formula would be to say I is equals to V minus E over RA, but um um but the motor is rotating at a different speed, and remember that E is what? Dependent, it's speed dependent. Let's say if the motor was not spinning at a constant speed, E is constantly changing. So please don't use this equation. Um, only only what you'll be given, guys, you'll be given the load current, or then you calculate the shunt current. Then this equation, this is basically the equation that we use to calculate the armature current. So guys, that is part one of this video series. The next section, please stay tuned. The next session I'll be doing questions. I'll be tackling calculations itself. So guys, I was just introducing you to the formulas and how we're going to apply them and what each value means, guys. Please, guys, like and share this channel to other people in your college, so that I can produce more content like this and help you achieve in excellence. Thank you.